Well, here's what we got going on today. I'll have the sub pass back your quizzes. That way you could look those over. You could ask each other any questions that you might have on those. Any questions you don't understand, I'll gladly make sure you understand them when I get back. There's going to be a skill check that I'm going to have the sub give to you. That way you can make sure that you're understanding this. The more practice that we get, the better off. And then I'm going to finish up the Riemann sums today. Last time we did it kind of in a table. I'm going to show you what it looks like calculus style. That way next time when I'm there, I can get away from the Riemann sums part of it and show you what it looks like calculus-wise. And then there is a book assignment. Heck, it might even be your last book assignment. Don't hold me to that, but it might be. But it's listed at the bottom of your class notes. But here's where I want to start at first. There's the answers to the skill check. So here in a little bit after you do your skill check, you can compare. You probably already compared with your friend, your neighbor, if you have a friend, and made sure they're right. But if not, there they are. You can always come back later and pause on that. But here's where I want to start. Look at your first example there. This is the exact same thing that we've done so far. I just kind of want to speed things up. Here's how I attacked it last time. I'd like to estimate the area under this curve right there using right bounded rectangles, so just memory serves you. The right side of each rectangle touches that. And then notice in this case my interval width is only 1, so that means I must be counting by quarters in this case. And I got that by taking the distance that I'm working with divided by the number of rectangles. So I knew that I needed to be working in quarters. And then remember, guys, on the right bounded rectangles, you won't use this number just to speed things up. So I know that each of these widths are going to be a quarter. And then to get the height of my rectangle right here, I need to go find f of 0.25, and then f of 0.50, f of 0.75, and f of 1, and I need to place those values right there. And I did that super fast for you, and I got these kind of numbers because I'm not going to punch in numbers during my video. That takes too long. And then, and then this came out to be 0.121, and 0.219, 0.295, and 0.25 for about an area of 0.885. That's what we did last time. And then guys, remember, if it's left bounded, the right endpoint won't be used. So this will really be f of 0, f of 0.25, f of 0.5, and f of 0.75. Each of these are still a quarter. And then I'm just going to copy some of these numbers over, but when I ran 0 through this, I got a height of 0 in this case. And then I got 0.484, 0.875, and 1.078. Then of course I had a 0, a 0.121, that's what I get for getting in a hurry, a 0.219, and a 0.295 for an area of approximately 0.635. It's an okay estimate. It's far from good though. So go down to your little area there. This is what it looks like calculus style. Here's what I'm trying to get you guys to. The fundamental theorem of calculus, which I'll talk more about next time. But this formula says all of this. This part right here, let me change this to white. This part right here, this antiderivative of a to b of f of x dx, that says we're going to find the area under the curve. From a to b, 1 to 3, 2 to 4, whatever that might be. I will show you what's meant by this here in a second. But the limit as n approaches infinity, I don't know if you remember that from your FST days, that's the Greek letter sigma, which means summation, which means we're going to add up. And then the n equal 1 to n basically means this. The more rectangles that we can shove in there, the more accurate we're going to be. So the more rectangles, the better. The bad thing, it's very, very tedious. But this says if I can go from 1 to n, the number of rectangles I'm working with, add them up, I'm going to get the area, which is just what we did. The x of I and the I represents the rectangle that we're thinking about. And I'll show you all this here in a second. But the rectangle that we're working with. The f of x of I represents the height of the rectangle. And then the only thing I really haven't talked about yet, the delta x, that represents the width of the rectangle. And then to get the width, I'm going to take the length of my interval, divide it by the number of rectangles that I'm going to be working with. And we're going to factor out this delta x today. And here's my thinking. If I had 2 times 1 plus 2 times 3 plus 2 times 5, notice that each of those has a 2 in it. That's equivalent to 2 times 1 plus 3 plus 5. So today I'm going to factor out my delta x. I'm just going to leave it out front. Makes it simpler. And then that's what I'm going to look at. Here, what I'm going to do now is I need to get out of this for just a second. And then I would like to show you this real fast. This is my Riemann sums calculator. But here's the first example that we're going to do on the back page. But here's our thinking. I've graphed the function 3x minus 1. And right now, guys, I told it to partition it with 4 rectangles. And my little calculator here will put them in as left-bounded, right-bounded, whatever I want. And notice up here it gave me what the sum is. But notice all of this space that's been wasted. So this isn't a very accurate approximation of the area. I'm going to come in and I'm going to make that 8 left-bounded rectangles. Over here you can see the new area. And notice that my waste has went down some. Well, 8's okay, but I'm going to come back in here and I'm going to look at 16 rectangles. If I do that, notice that the waste is getting a little bit smaller again. And over here you can look at my new area. Really, where am I going? 1 to infinity says the more rectangles you can put in here, the better you're going to be. Bernard Riemann did this by hand over and over and over. It was nothing for him to put 100 or 200 rectangles underneath the curve to see how accurate he could get for the area. But there it is with 32 rectangles. Notice my new area, 9.8125. You could say, well, that's pretty darn good. Nothing magical. I'm just doubling these because I can double numbers in my head. Notice that my rectangles the width is getting a heck of a lot smaller. But notice that my new area, but notice all this waste. It's almost getting down to a minimum. Well, I could look at whatever number you want me to type in, 128 rectangles. There it looks a little better. I could look at 256 rectangles. So not a ton of waste now. I could go ahead and look at 512. There's the limit concept of it. The more I do, the more accurate it's going to be. So there, finally, they got so close, we wound up coloring this in, basically. That's where that part of the formula 1 to infinity goes. So I've already filled that part out. Here goes your examples. I'll show you what I got now. It's the exact same thing that we did last time. I'm just going to try to speed it up a little bit now. Let me go back to some black ink here since I'm on the white. I'd like to find the area under the curve of 3x minus 1 from 1 to 3. So really, here's what we're finding. If we were to graph it, I've got this line, basically. And we're trying to find that area in here. Well, here goes the thinking. If I'm going from 1 to 3, that's a unit of 2, and I'm going to place 4 rectangles in here. Well, the width of each rectangle then is going to be 1/2. I'm going to go 3 minus 1 divided by 4. Tells me that delta x is 1/2. I set up a chart. If you got a better way, set up however you like you think you got a better way, but I need to talk about 1 rectangle, 2 rectangle, 3 rectangle, 4 rectangles. X of I is going to be the endpoint that I'm going to run through the equation to get my corresponding height. Remember, since it's left bound, my right endpoint won't get to come out and play. So if I'm starting at 1 on my left, counting by halves, I'm going to run a 1 through my equation, then a 1.5, and then a 2, and then a 2.5. This gives me the x value that I need to run through. This will give me the height of my corresponding rectangle. So I'm going to run 1 through the rectangle, or through my equation up there, and I'm going to get 2, 3.5, 5, and 6.5. What I really found right here is the heights. So to estimate the area from 1 to 3, it's just going to look like this. Delta x is 0.5. And then I need to add together the height of the first rectangle, the height of the second rectangle, the height of the third rectangle, the height of the fourth rectangle. I need to run that through, and I'm going to get about 8.5 units for the area right here. We looked at that a while ago with the calculator. That's okay, but it's far from exact. If you think about the right endpoints, I'm still going to use 4 rectangles. If I'm looking at the right endpoints, remember the 1 doesn't get to come out and play this time. So I need to run a 1.5 through the equation, then a 2, a 2.5, and a 3. When I did that, I got 3.5, 5, 6.5, and 8. So to estimate the area under the curve, I'm going to have delta x, which is 0.5, times the height of each rectangle. The height of the first right bound rectangle happened to be 3.5, and then a 5, and then a 6.5, and an 8. So using right bound rectangles, it was about 11.5. So okay, nothing great, but okay. Using the midpoints, once again guys, I got 4 rectangles. The values I need to be running through though is I'm starting at 1, counting by a half. So if I think from 1 to 1.5, the first number I need to run through there then, I need to run 1.25 through there, because that's the midpoint between those two numbers. And then I'd use a 1.75, a 2.25, and a 2.75. Basically, we're doing exactly what we did 2 classes ago, just calculus style. And I'm not setting up that chart for you. On your assignment, you'll get to come up with your own means. The height of each of these rectangles then 2.75, 4.25, 5.75, and 7 1/4. I jam myself on room, so what I'll do here is this. The width of each of these is 0.5, and I'll sum up those. So 2.75 plus 4 1/4 plus 5.75 plus 7 1/4. And then when I did that, I got right at 10 for that one. So it's the exact same thing we did, just think through this. As soon as I saw left endpoint, I knew that this number doesn't get to come out and play. As soon as I saw right endpoint, I knew the 1 doesn't get to come out and play. Here's kind of the same thing on my next example, but I'll just click right through it. Really, I'm going to look at the curve 1 over x from 1 to 4. So here's really what we're trying to find. If I sketch you a rough graph of it, when x is 1, 1 over 1 is 1, so I'm going to let this be 1. When x is 2, I'm going to get a half. 3 and 4, we're going to be looking at the area under a curve, something like that. So this is the area that you're going to be finding. But the thinking is going to be just like what we did. I'm going to go from 1 to 4, so let me get delta x out of the way first, the width of each rectangle. Delta x is going to be 4 minus 1 divided by the number of rectangles that we're doing. And on your sheet I had n equal 4 again, so divided by 4. So for these examples, delta x is going to be 0.75. I'll click through the numbers for you. Once again, I don't know why I picked on 4 rectangles, maybe because that seemed the less tedious and less boring for you guys. When I'm thinking about my left endpoints, the 1 gets to play, the 4 does not. So the first endpoint I'm going to run through is a 1. My delta x is 0.75, so I'm going to run a 1.75 through there, a 2.5, and a 3.25. When I did that, I had a 1, a 0.57 about, a 0.4, and a 0.31. I'm running them through this equation right up there. So my area is going to be the width of each rectangle, 0.75, times the 1 plus the 0.57 plus the 0.4 plus the 0.31. And I had about 1.71. And if you think about your left endpoints, I'm going to be high. That's going to be kind of a high estimate. But to keep things clicking, when I go look at the right endpoints, once again, guys, I got 4 rectangles I'm going to be looking at. When I think about the right endpoints, this time the 4 will get a play, but the 1 won't get a play. So the 1 doesn't get a play, but the next number I'm going to use then is 1.75, 2.5, 3.25, and 4. When I ran those through, I had 0.57, 0.4, 0.31, and 0.25. So the estimated area, the area of each rectangle, 0.75, times the sum of those numbers. And when I approximated that, I had about 1.15. You probably got the hang of everything by now. If you do, shut her off and then get busy. If not, let me finish up the midpoints then. I still have 4 rectangles. Remember, if you list these out, I'm going 1, 1.75, 2.5, 3.25. So when you get your midpoint, this plus this divided by 2. 1 plus 1.75 divided by 2 tells me I need to run 1.375 through my calculator. And then 2 ways. You could add 0.75 to this to get your next midpoint, or you could add these 2 things together, divide by 2. Whatever you do, these are the numbers that I'm running through, and 3.625. I ran them through the 1 over x, so I had 0.73 approximately, 0.47, 0.35, and 0.28. To bring it home, the width of each rectangle is 0.75. Sum those up, and I had about 1.365. Okay. Hey, so if you think about it, guys, not a hard lesson at all. Tedious is it. You will enjoy next times much better. So here's what I got you doing assignment-wise. I've got you doing those problems. These I didn't do any like, but these are geometry kind of problems. If you will, graph it, shade in what you're going to find the area of, and use some geometry formula. A semicircle, a triangle, a trapezoid, whatever the heck we got. So, and 24 is going to be tedious, so not a ton of problems. You should have a ton to work on them if you choose to use your time that way. So good luck. I'll clean up any questions that you might have next time. Have a great day, guys.